Look up on a clear night, and everything seems still. The stars hold their places. The Milky Way arches overhead like a frozen river of light. But this stillness is an illusion. Right now, as you read these words, our entire galaxy is racing through space at more than 600 kilometers per second. That is over 2 million kilometers every hour. In the time it takes to blink, we have already traveled the length of a country. Our galaxy is not a fixed landmark. It is a city of 200 billion stars, thrown across the darkness toward a destination we did not choose. And here is the strange part. This motion has a direction. It is not random drift. Something out there, far beyond the reach of our telescopes, appears to be pulling us. The Sun carries its planets around the galactic center once every 230 million years. The galaxy itself orbits within its local group, but layered on top of these familiar movements is a deeper, faster current, sweeping the Milky Way, Andromeda, and dozens of neighboring galaxies, all in roughly the same direction. Picture a vast, invisible tide. We are caught in it. Whatever is causing this flow must be enormous, a concentration of mass so great that its gravity reaches across hundreds of millions of light years to tug on our galaxy and everything near it. For decades, astronomers gave this unseen influence a name that captured both its power and its mystery. They called it the Great Attractor. But naming something is not the same as understanding it. Where is it? What is it made of? How can a single region of the universe command the motion of thousands of galaxies, including our own? The answers would take half a century to assemble, drawn from measurements no human could ever feel with their own body. We do not sense the speed. There is no wind, no rushing sound, no sense of falling. The earth beneath your feet feels solid and calm. Yet we are moving, and something is drawing us onward. The first challenge was simply to prove that this motion was real, and to measure a speed no instrument on the ground could detect directly. How do you measure the speed of something you cannot feel, with no fixed point to measure against? The universe offered an answer no one expected. In 1964, two radio engineers at Bell Labs, Arno Penzias and Robert Wilson, detected a faint hiss coming from every direction in the sky. It was the cosmic microwave background, the afterglow of the Big Bang itself, radiation released 380,000 years after the universe began. This ancient light fills all of space, a uniform glow at about 2.7 degrees above absolute zero, and it became the ultimate reference frame. In the 1970s, astronomers realized that if the Milky Way were truly motionless, this background radiation would look identical in every direction. But it did not. On one side of the sky, the glow appeared very slightly warmer and bluer. On the opposite side, cooler and redder. This pattern is called the dipole. It is the fingerprint of motion. Just as a moving car compresses sound waves ahead of it and stretches them behind, our galaxy compresses and stretches this primordial light as we plow through it. From the size of this temperature difference, roughly 1 part in 1,000, astronomers calculated our speed. The result was staggering. The Milky Way and its local group are moving at around 600 kilometers per second relative to the cosmic background, toward a point in the southern sky near the constellations Centaurus and Hydra. Here the puzzle deepened. Scientists added up the gravitational pull of every known galaxy in our neighborhood. Andromeda, the Virgo cluster, the familiar landmarks of the local universe. Together they could account for only a fraction of this motion. The numbers did not close. Something far more massive, far more distant, was doing most of the pulling, and it lay in a direction where the maps were nearly blank. The dipole told us how fast and which way. It could not tell us what. To find the source, astronomers would need to trace not just our own motion, but the motion of thousands of other galaxies, searching for a pattern in the flow. And when they finally mapped that pattern, it pointed like an arrow toward a single, hidden region of the sky. In the early 1980s, 7 astronomers set out to map the movements of galaxies across the sky. Officially, they were studying elliptical galaxies. Unofficially, the astronomy community gave them a nickname that stuck: the Seven Samurai. Their names included Sandra Faber, Donald Lyndon Bell, David Burstein, Roger Davies, Alan Dressler, Robert Jean Terlovich, and Gary Wegner. Their method was ingenious. To measure how fast a distant galaxy is moving, you first need to know how far away it truly is. They developed a technique using the relationship between a galaxy's brightness and the motion of stars inside it, allowing them to estimate real distances independent of redshift. By comparing the true distance to the apparent velocity, they could isolate the extra motion, the peculiar velocity, caused by gravity rather than by the general expansion of the universe. What they found was not random. Hundreds of galaxies across a huge swath of sky were not simply drifting apart with cosmic expansion. They were streaming together, coherently, like a school of fish caught in the same current. The Milky Way was part of it. So was our entire local supercluster. All of it flowing in the same direction, toward the constellation Centaurus, at speeds of hundreds of kilometers per second. This was the confirmation. The dipole had shown our own motion. Now the 7 Samurai revealed that thousands of galaxies shared that motion, all pulled toward the same invisible region. In 1986, Alan Dressler gave the source a name that would define the mystery for decades. He called it the Great Attractor. It sounded like something from science fiction, but the science was solid. Somewhere out there, at a distance of perhaps 150 to 250 million light-years, lay a concentration of mass so vast it was steering the traffic of the local universe. The flow pointed to it like a compass needle. But when astronomers turned their telescopes toward that exact patch of sky, they hit a wall. The direction of the Great Attractor lay almost precisely behind the densest part of our own galaxy, a region choked with stars and dust. The very thing pulling us was hidden by the thing we live inside. To see it, they would first have to see through the Milky Way itself. Our galaxy is a flattened disk of stars, gas, and dust, and we live inside it. When we look out toward the Great Attractor, we are looking straight into that disk, through the thickest curtain of matter in our sky. Astronomers have a name for this blind spot. They call it the Zone of Avoidance. It is not a small gap. The band of our galaxy's plane obscures roughly 20% of the entire sky, a fifth of everything there is to see. Behind that band, thousands of galaxies are hidden. The problem is dust. Clouds of interstellar dust and dense fields of foreground stars absorb and scatter visible light, especially the light of distant galaxies far beyond our own. A galaxy sitting behind the galactic plane can be dimmed by many magnitudes, its light swallowed before it ever reaches us. Early galaxy catalogs, built from optical photographs, simply had a blank stripe running across them, a region mapmakers had learned to avoid. And here lay the cruel irony of the Great Attractor. Of all the directions in the sky where its source might have hidden, it lay almost exactly behind this obscured band, low in the southern constellations of Centaurus and Norma. The arrow of the cosmic flow pointed directly into the one place our instruments could barely penetrate. Imagine trying to identify a mountain range on the horizon while standing in a dense fog. You can feel the pull of gravity, you can measure the streaming of galaxies all around you. But the object responsible remains veiled behind the very structure you inhabit. For years, this made the Great Attractor as much a frustration as a discovery. Scientists knew it had to be there. The mathematics of the flow demanded a huge mass in that direction. But confirming it, weighing it, seeing what it actually was, required a way to look through the dust rather than around it. The answer would not come from ordinary telescopes gathering visible light. It would come from wavelengths the dust could not stop. Radio waves, infrared, X-rays. In these hidden colors of the universe, the veil of the Milky Way would finally begin to thin, and the galaxies behind it would emerge from the fog. The dust that blocks visible light is nearly transparent to other wavelengths. This became the key that unlocked the zone of avoidance. Through the 1980s and 1990s, astronomers turned to the parts of the spectrum that could pierce the veil, and slowly, the hidden sky behind our galaxy came into focus. Infrared light was the first breakthrough. Longer than visible wavelengths, infrared slips past dust grains that would scatter ordinary starlight. In 1983, the IRAS satellite surveyed the entire sky in the infrared, revealing galaxies that optical telescopes had never seen. Later, ground-based surveys mapped these hidden galaxies in detail, and the blank stripe on the maps began to fill with points of light. Radio astronomy pushed even deeper. Neutral hydrogen gas, the raw material of galaxies, emits at a wavelength of 21 centimeters, a radio signal that passes through dust as if it were not there. Using instruments like the Parkes telescope in Australia, astronomers surveyed the zone of avoidance for this hydrogen signature, detecting entire galaxies purely by their radio glow, their optical light, forever hidden behind our own. Then came X-rays, and they revealed something the other wavelengths could not. Galaxy clusters, the largest gravitationally bound structures in the universe, are filled with gas heated to tens of millions of degrees. This gas blazes in X-rays. Satellites like ROSAT, launched in 1990, scanned the sky in X-ray light, and where clusters lurked behind the dust, they glowed like beacons. When astronomers combined these views, infrared, radio, and X-ray, a structure emerged directly in the region of the Great Attractor. There, low in the southern constellation of Norma, deep within the zone of avoidance, sat a massive concentration of galaxies. It had been catalogued decades earlier as a faint smudge, given the designation Abell 3627 in George Abell's cluster survey, but its true importance had been invisible. Now the new wavelengths showed it clearly, a rich, dense cluster of hundreds of galaxies, right where the cosmic flow pointed. The Great Attractor was no longer just an inference from motion. It had an address, and a name emerging from the dust. Astronomers called it the Norma Cluster, and they turned their full attention to weighing exactly what they had found. When the dust finally parted, one object stood at the center of the crosshairs. Catalogued as Abell 3627 and named for the southern constellation Norma, it sat almost exactly in the direction the Seven Samurai had traced years before. In 1996, astronomer Renée Croncourt-Weg and her colleagues confirmed what the radio and X-ray data had hinted. A rich, massive galaxy cluster lay hidden roughly 220 million light-years away, buried behind the brightest, dustiest band of the Milky Way. It had been sitting in plain sight, invisible only because our own galaxy stood in the way. Norma proved to be enormous. Hundreds of galaxies swarmed within it, bound together by gravity, their motions betraying a total mass equivalent to roughly 10,000 trillion suns. X-ray telescopes revealed clouds of gas heated to tens of millions of degrees, trapped in the cluster's deep gravitational well. Here, at last, seemed to be the beating heart of the Great Attractor. Its position matched. Its scale was staggering. For a moment, the mystery appeared solved. But when astronomers did the arithmetic, the numbers refused to close. Norma was massive, yet not massive enough. The cluster could account for only a fraction of the pull, dragging the local group at more than 600 kilometers per second. Measured against the velocities of galaxies streaming across hundreds of millions of light-years, Norma's gravity fell short. Something else, something larger and farther, had to be reaching across the void. The Great Attractor, it turned out, was less a single object than a signpost. Norma marked the crowded intersection of a vast overdensity of matter, a region where galaxies clustered thickly along the cosmic web, but the streaming motion pointed beyond it, through it, toward a concentration even more distant and more massive than the one now revealed. Astronomers began to suspect that Norma was merely the near edge of something they had not yet fully mapped. The Great Attractor was real, but it was not the destination. It was the doorway. And on the far side of that doorway, deeper into the obscured southern sky, lay a structure so immense it would dwarf everything found so far. Look past Norma, farther along the same line of sight, and the galaxies keep coming. At a distance of roughly 650 million light-years, 4 times deeper than the Great Attractor, astronomers found the largest concentration of mass in the nearby universe, the Shapley Supercluster. Named for Harlow Shapley, who first noted an unusual abundance of galaxies in this direction in the 1930s, it was only in the following decades that its true scale emerged. Shapley is not a single cluster but a colossal assembly of them, more than 20 rich galaxy clusters woven together, containing tens of thousands of galaxies. Its total mass may exceed 10 million billion suns, an overdensity so extreme that it stands out even against the vast averages of the cosmos. Aligned almost perfectly behind Norma, it lies in the same broad direction as our motion through space. That alignment changed the picture entirely. The Great Attractor, once imagined as the final answer, now looked like a way station on a much longer journey. Measurements from the 2000s suggested that a significant share of the local group's velocity, perhaps a quarter or more, could be traced to Shapley's distant gravity. The pull we feel was not local at all. It reached across 2/3 of a billion light-years, tugging our galaxy toward a cosmic metropolis we may never approach. Yet even Shapley did not fully close the account. Astronomers, summing the mass of everything they could see in that direction, still found gaps between prediction and observation. The flow was too fast, too coherent, to be explained by any tidy list of clusters, however grand. Something in the accounting remained missing. It became clear that our motion could not be assigned to a single culprit. Norma pulled. Shapley pulled harder and from farther. Between and beyond them lay filaments of galaxies, threading through darkness. The Great Attractor had become a name for a direction, not a thing. To understand where we are truly heading, astronomers would have to stop hunting for one object and start mapping the entire landscape, the full architecture of matter, and the great emptiness that shapes it just as powerfully. By the 2010s, a new map emerged, one that abandoned the search for a single attractor and instead charted the flow itself. In 2014, R. Brent Tully and his collaborators traced the velocities of thousands of galaxies to define the boundaries of the supercluster we inhabit. They called it Laniakea, Hawaiian for immense heaven, a structure spanning 500 million light-years and holding the mass of 100,000 trillion suns. Within it, all galaxies drift along converging streams, like water flowing downhill toward a common basin. The Milky Way lies near its outer edge. This map revealed that matter in the universe is not scattered randomly. It gathers along vast filaments, threads of galaxies stretching across hundreds of millions of light-years, meeting at dense knots like Norma and Shapley. Between these threads lie the voids, enormous cavities nearly empty of galaxies, some spanning hundreds of millions of light-years of near-perfect emptiness. This is the cosmic web, and our motion is its signature. Then came a discovery that reframed everything. In 2017, researchers led by Yehuda Hoffman identified not just a pull, but a push. Behind us, in the direction opposite Shapley, lay a region strikingly empty of matter, which they named the dipole repeller. Emptiness cannot exert force, but relative to the denser universe elsewhere, an underdense region acts as though it repels. Where matter is thin, gravity is weak, and galaxies drift away from the void toward richer surroundings. Our galaxy, they found, is being pushed from behind by the dipole repeller and pulled from ahead by Shapley, the two effects combining to drive our motion. Suddenly, the Great Attractor was only half the story. We are not simply falling towards something. We are also fleeing from nothing, sliding down a gravitational slope shaped by both the crowded regions and the empty ones. Attraction and repulsion, matter and void, working together across a billion light-years. The mystery that began as a hunt for one hidden mass had opened into something far larger, a portrait of the entire universe as a single dynamic structure, and our small galaxy riding its currents. So where is the Milky Way going? The honest answer is that we are carried, not steered, drawn along by a landscape too vast for any single feature to command. When astronomers first detected our 600 km/s drift in the cosmic microwave background, they imagined a hidden mass, a great attractor waiting to be named. The search led them through the Zone of Avoidance, past the veil of dust to the Norma Cluster. It led beyond Norma to the towering Shapley Supercluster. And it led, at last, to a truth larger than any of them. No one object owns our motion. The Norma region contributes its share. Shapley, 4 times more distant, contributes more. The dipole repeller pushes from behind. The filaments of Laniakea guide the flow, and the voids between them shape it as surely as the clusters do. Our velocity is a sum, an average of countless tugs and pressures spread across a billion light-years of cosmic structure. We do not travel toward a destination so much as we ride a current, the slow gravitational settling of matter across the largest scales that exist. Consider what this means. Every measurement, every survey in radio, infrared, and X-ray, every velocity map of streaming galaxies, has revealed not a monster in the dark, but a network, a web of matter and emptiness in which we are a single strand. The Milky Way, home to 400 billion stars, is itself just one traveler in a migration involving the entire visible universe. The Great Attractor was never a place we could reach. It was the name we gave to our own ignorance, a marker for forces we had not yet learned to see. Now, having mapped the flow, we understand our motion as the outcome of everything, the combined influence of all the matter and all the voids across the observable cosmos. It is a humbling picture and a magnificent one. We are not being seized. We are being carried by the shape of creation itself. In the end, the deepest lesson is written across the whole sky. No single hand pulls the Milky Way.